Anyways, yeah, right. So this is the third class on complex functions, complex numbers, complex functions, and seeing differentiability of complex numbers. So this, as I've explained earlier, can be useful in the theory of polynomials especially. But currently we're just going through the theory before we can apply it in polynomials and so on. So let's see what we can do. So differentiation. Yes. Oh, sorry. No. Yes. One second. Differentiation of complex functions. One second. So we have at length seen about differentiation of functions from R to R. Right? Differentiate, but now we'll try to see differentiation of functions from C to C. While doing this, we can keep one, I think, major goal in mind, which will help you to see these things in context, because this is a slightly theoretical topic today's. Okay, so one may get lost into why are we defining the things we are defining and so on. So one major thing would be, I mean, so I assume all of you know what's the definition. Okay, let me just go over that once very quickly. So f is a function from C to C. You can just take it from C to C, though to be more specific, maybe we can be that f is a function from this omega to C. Now, what is omega? Omega is a good set. Okay, it is what is known as an open connected set, but you can just treat it like a ball. There's a lot to be said about that kind of set, but that I feel is not our top priority right now. Okay, that will not really help us too much. But omega is a set which is, you can, maybe I can draw a slightly better picture, something which doesn't have a boundary. You see what I'm trying to say? You can take it like an open ball but doesn't have a boundary. What do I mean? So omega is like this. Now what do I mean? I mean that if you take a point inside omega, then you will always be able to extract an open ball, or you'll always be able to move a little bit and still remain in omega. Okay, it is just the correct analog of an open interval. Right, an open interval, anywhere you are, you can draw a small neighborhood, and we know that being able to draw that neighborhood was essential to define differentiability and so on, right? So that's why we want it to be an open interval in an open ball in most cases, or an open set, which is basically at any point inside you can draw a ball which is inside the set. That's the definition of an open set. That's the property we want omega to have, and it's very clear that it's a good property to have. But there is another property which we want omega to have. So omega is open. So open means any point you take inside it, you can draw a small ball which is still inside. There are other ways to say it, but this is one way to say it. Another property which is again very essential, which we don't quite appreciate it, because we till now have been doing local differentiability at a point. But I think all of you would have seen mean value theorem and so on, very essential theorems, right? There, or even if you look at continuity, we have extreme value theorem, intermediate value theorem. In all those, we do our job on an interval. Everybody agrees with me, right? We do our job on an interval. We don't have domains like union of two open intervals which are disjoint. This kind of domains we don't use when we are talking about intermediate value theorem. It will not hold. Intermediate value theorem will not hold in this case, or we take closed also, doesn't matter too much. The intermediate value theorem will not hold for this kind of things, right? So that's why we want some sort of a connectivity. Now I'm not going to define what's the connected set and all, because that will take us away from the point. Maybe we'll do that later. But the other thing is that we want connectivity. In two dimensions, it becomes very of utmost important. Basically, your shape, whatever it is, it must be open, but there must not be a split in that anywhere. Okay, from any point you should be able to go to any other point by a path or something like that, roughly speaking. Okay, right. So It's not concave convex. It's much more general than that. And of course, in lot of for a lot of theorems, we'll have to add that condition of convex and concave. But these shapes are much more general. There could be any weird shape like this, which is not convex. But never, we don't need to worry about that too much here. Okay. All right. But it should be connected. Again, I'm not going to the definitions, but just to so you know that why we are putting this definition. Okay. Right. So now we can come back to the definition. Now, I suppose we all know the definition, but we can still just take it. So f is differentiable, but here we'll use the word holomorphic. Again, there's a certain reason why we do this. We'll see. Holomorphic at z naught if this limit. So this is important. Z going to z naught, or if you want h going to 0, it's the same thing. It will be the same thing. H going to 0. F of z naught plus h minus f of z naught divided by h. This limit exists. Right. So what does h going to 0 mean? It means that this h will be in this neighborhood and h can take all the values in that neighborhood. Okay, h can take all the values in that neighborhood. H is not a real number. H is going to 0 here would mean that mod of h is less than equal to epsilon. Something like that. Okay. So one can even break this down further. This limit being L, okay, means that this quantity g of h can be made epsilon close to L if h is delta close, if h is delta close to 0. Okay, so if you want an epsilon, then you can find a delta such that whenever h is small enough, but here small enough is a very strong thing. It is not just small on the interval, not just small values on the interval. It's small values in this entire ball. So there's a lot of tests, tests that the function has to pass through in order to be declared differentiable. You see my point? Yeah. So h can be like this, h can approach like this, h can approach diagonally. It has to, on all the values, this has to be less than epsilon gh minus. So that's a very strong, if that happens, it means it's a strong thing, right? It's a very strong thing if that actually happens. But it happens for a lot of functions, and those functions are called holomorphic. Okay, so I'll just go back to just saying this exists. Okay. So is it okay? Now we can move on, right? So now that we have the definition and we saw just a quick recap of the example, we saw that fz equal to 1 by z bar, sorry, not 1 by z bar, fz equal to z bar. We saw that this was not differentiable, right? I suppose all of you know that. If someone wants me to review that, I can do it. It was not differentiable. Yeah, it's fine. Yeah, so this is not holomorphic. And that is because of this very strong condition, right? It is not, so it is not, so we are not saying that limit of the mod exists. That is slightly easier thing because it becomes a real number, right? But this as a complex thing is limit should exist. That is a stronger thing, right? Because that means that this thing minus L uska mod must be less than epsilon. That is a stronger thing than saying that mod of this minus L is less than epsilon. That's easier to happen, like because mod A minus mod B can be less than epsilon, but mod of A minus B may not be. In right, this doesn't follow from there, right? But if this is less than epsilon, then that implies that the earlier is true. So it's a strong thing. And also we are moving in H can move in complex. That's actually H. Yeah. No, not just along every line. It could be curved lines and all that. Right. So H, when you're saying H is close to 0, I mean, it could be anything, right? It could be along a parabola. You could approach, you can take a sequence along a parabola. Like you can just take the sequence of you can just take the sequence. I mean, you can take just fz equal to z square, right? That sequence. I mean, you can take h to be 1 by n square, right? That sequence. You can take h to be 1 by z 1 by you can take 1 by 1 plus I n square, something like this. Its mod goes to 0, but this doesn't approach on a line through a parabola. So there are uncountably many possibilities. Okay? Right. And yeah, please, yeah, say.
Would it be means enough if I can come up with that along every line, means along every diameter of this circle, when h is approaching zero along every diameter of the circle, and this condition holds, and then can we say it is convergent?
That's a very good question. So your question is it enough to check along all diameters? So is it enough to check for hn equal to some line, right? Hn equal to lambda, any vector, right? Any vector, lambda z. Yeah, lambda z. So the z doesn't change, but the lambda changes, right? So maybe something like this. Is it enough to take h like this? So this is not a sequence; it's just a line, okay? That it just as lambda goes to 0. So is it enough to take lambda going to 0 and things like these? No, in fact, that is not true. But it will be hard to come up with counter examples. Think about it. So think about a function in which
Only taking lambda z would give us with only one diameter. That was
no,
only
no,
one.
yes, yes, I understand. Yeah. So yeah, what I meant is for all z. Yes, that's what I meant. Yeah, that if each of these limits exist and if they are all equal, uh, okay. Now if each now that's a complicated question. So if each of these limits exist, so if you take suppose for all z, right? So you fix a z and you do this, and the limit exists. This limit exists, and if you change the z and still the limit exists, this happens for all z. Uh, if this happens for all z, does it imply? No, that does not. I do not think that will imply holomorphicity. That will still not imply. And roughly the reason will be like this. But I don't have a counterexample off the head. It will be a complicated example. It will be something like this. So suppose you take z to be this line, z1, and let's say you take z2 to be this line, you take z3 to be this line, and so on. Okay. Now suppose your epsilon is some 1 by n, right? And so for this z1 to attain, so you fix epsilon greater than 0. Now for this z1 and for this particular epsilon and this particular z1, you need delta to be, let's say, half. Let's say you need delta to be half. Okay, 1 by 2. And for this one, the smallest delta is, let's say, 1 by 3, right? And for this one, let's say the smallest delta is 1 by 4. Then you cannot find the delta. Does my point make sense, right? For z1, the smallest delta that you need is half. More than half, if you put the value more than half, then more or half times z will not work. Like half times z will not make this less than epsilon. Okay. And then for z2, let's say you need 1 by 3, and then for z4 you need 1 by, for z3 you need 1 by 4, and so on. So you're needing smaller and smaller deltas, and so this will obviously you cannot find a delta which works for all. And in the end, clearly you need a delta which should work for all. Is that right? I mean, because given this epsilon, you will need a delta ball. You will need a delta ball, and everything inside the delta ball should work. But if you take a delta ball of size, let's say 1 by 100, there will be z 101. There will be z 101, which will say, no, I need a delta to be 1 by 101. 1 by,
PHP algorithm.
you can, it's not even a pH. It's not a PHP. It's more straightforward than PHP, right? It is just that you need smaller and smaller deltas, but you really can't have that, right? Right. But in the end, everything is working because h is small enough. Sorry, because you need a delta such that in the entire ball it should work. That's the definition, right? But that it's not guaranteed because of this. And so you can now even guess what kind of function this should be. It should be kind of a spiraling up function, some sort of function that, I mean z1. So if you have this function from c to c, you can consider this function from c to r2, but then you can just consider the first r of it. You can, I mean, this is two parts, right? C to r2, two components. So you just take one of the components, right? And along one of the components, the function would be like this. It would spiral up at an infinitely fast rate. So it would be like this. So if you take z1, so at z1 it would have a reasonable height, but then when you go to z2 the height will increase and the height becomes infinite as it goes inside, something like this, right? And it's, sorry, I mean, it should not take so many turns. I mean, in fact, just in actually in one turn it should, you see, in one turn, so I'm just turning around the z axis, right? In one turn it should blow up in one. And you can easily construct such a function. You can take some tan function and just maneuver, just change it in. It's very hard to draw. In one turn it should become infinite, because then you will always have these, when you come here to some z100, it would shoot up here, so you need a very small, and then you need smaller balls for the z is once the I increases, right? And this will not, and it's obviously not holomorphic also, right? So in fact, forget about holomorphic. I mean, this kind of function will not even be real differentiable. That is a different, easier concept. So we'll see that, and that is a concept we'll have to see, and which is actually more in spirit of what we have been doing, and that concept will help us to answer this. Okay, right. Others have questions here? Those who are here today.
Sir, in the spiral thing,
Hmm.
I did not really understand how you said that it is. I mean, it's connected to.
Yeah. Yes. Yes. So let's see it here. So first of all, in this one, let me say this one again, because I think then it will make this clear for me also, I think. Let's see this one. So
What is the type of the function that you're considering?
oh yeah, so the function is from complex to complex. Okay,
Oh, okay.
right. So the input is complex and the output is also complex, right? So we are trying to see. So basically, you can look at that. This, you get a function gh. So this is your function gh. Okay, and we are just trying to see. So now it's not even about differentiability. It's just a function gh whose limit you're trying to understand at zero, as h goes to zero. Okay. Now, if we are given that along any line, if you take a line, you fix z and you take a line, so along any line, which means that if h is of the form lambda z, if h is of the form lambda z, and you let lambda go to zero, then this thing works. This is given.
Okay.
So for any z this happens. Okay, so for, let's say that for z1, so maybe we should write it here. Yeah, this can be made into an interesting problem. So limit lambda going to 0, g of lambda z1 is equal to L. Okay? This means that you are approaching along that line. It has made it into, because the z is constant, the z is not changing, only the lambda is changing. It's like a real function only. Now also it is given that limit lambda z2 is also L. Okay, so you take a different line. So z1 for approaching along z1, as you are going, as the values are becoming smaller but remaining on z1, the limit g is also going towards L. And similarly, if you approach along z2, then also it's happening. And similarly for all by this time it's clear for all z. Let's say for all zi's it happens. But the problem is that the different zi's might demand different deltas for a particular epsilon. Okay, so at this point you fix an epsilon greater than 0. Now the problem is that for this epsilon, z1, yeah, yes,
And the thing where you said we will be getting different values of delta for different z, the closed interval on which delta could residing of different z i's, right?
Hmm.
Can I frame it like that?
No, it will not be a closed interval. It is just varying.
Means if we could frame it means uh, frame it like this that uh, for different z i's there will be some closed intervals in which the delta could overcome that. So that interval will be such that this condition will
Yes, 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 yes. Then,
so then from there we can get a decreasing differential
yeah, okay,
closed intervals with decreasing by decreasing with the diameter of the
okay,
circle.
yeah, yeah,
Uh, but there's a theorem no, that it says that if we get if I have sequence of closed intervals with
hmm.
decreasing diameters, then their unions give us only single point.
The intersections. I mean, union will never give you a single point. Right? Yeah, yeah. But the problem here is that the intersection might be zero. That's why we are worried. So you are thinking that you'll get a smallest delta by taking the, yeah, but that smallest might be zero. So okay, so let me come to that in this argument. Okay, so I think it gave us some time to think about this, so it's good. So this so you see, for each zi has a different delta requirement. Okay, so for a particular epsilon, so for a particular epsilon you demand, of course, again, just simply, sorry, you demand this to be less than epsilon. But each zi, so for zi, the delta I might be at least 1 by I, right? Okay, like for z1, delta 1 would work. For z2, delta 2 would work. A half would work, and not less than that. And for z3, more lesser delta might be needed. And for z4, lesser delta even might be needed, right? For this to be satisfied. Okay, is it okay? Now the problem is that this sequence of smallest deltas doesn't have a smallest, right? Its smallest is zero, right? So there is no smallest delta, right? Now, because there is no smallest delta, this function will not be differentiable, because for the function overall to be differentiable, for this epsilon, you need a delta ball. But if you're going to take a delta ball, right, then some z million will come, right? Some z million will come, and it will say, no, I need 1 by 1 million, and this delta may be bigger than 1 by 1 million, right? That z of, so let's say, I will not say delta, let's say you take delta to be very small, let's say you take 10 to the power 10, then I will bring in 10 to the power 10 plus 1, and this will say, no, I need a delta to be smaller than that, right? And then it will not work, right? Then this will means you don't have that delta, then you'll take a smaller delta, but then a bigger z will come, and it will say, no, I need a smaller one. So there is no smallest delta. That was the whole point. There is no, I mean, it's on the face that there is no smaller delta. No theorem can save you here. It's clearly not working. Now, do you see how this is related with spiral? Because now obviously I cannot draw a spiral function from c to c, and that is, well, it's possible to draw, but then I have to draw two pictures. Okay, but I'm saying that, or let's not say that, let's change it. Let's say that now you're looking at, so let's say this is the domain. So what I've drawn here, let's say, is the domain. Okay, you can take the range here. Now how would the range of that function look like? My claim is it will look like this. On z1 region, the range, so this red one is the range values. Okay, it's fairly good, but then I should have to pull it up a little bit. See here, near the z1 range it is fine, but as the function moves on a circle, it kind of becomes like this. Does this make sense? The value increases. The mod value increases, sort of, right? This gzi. I mean, you can just, let's say L is zero for the time being. Maybe that was wrong. What I say? Yeah, if you can assume L is 0, that's not a point. You can always shift it and consider the shifted function. Okay, that's fine. Let's say L is 0, and that's fine. You see, this kind of function is a counter example, right? Because when you take z1, fine, but when you come to z this, then lambda has to be very small, right? Because it kind of is becoming very big, right? I mean, the image is here, right? So uh, 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 I mean, my point is that the function will not be like, I mean, the function cannot be like this, right? My point is that this is the value at z of, let's say, 10 to the power 10. Okay, so to pull this inside, to pull this inside the epsilon ball, right? To pull the jeeves inside the epsilon ball, you have to attach a very small delta to it, right? I mean, this cannot be the graph of the function, right? This is just the output values when you take the input values along the zi's, right? When you take the input values along the zi's, so maybe I should draw yeah, because I'm not prepared. The point is, yeah, along the zi's is like this, so right. And so for this, sorry, 1 second, something else opened. Yeah, yeah, so it's like this, like along z1 it is fine, along here it's already becoming bigger, so you need to bring it down by taking a smaller delta, assuming that the function is like that, it comes down as you bring it out, you can arrange that, and here it gets bad. Okay, is this more clear now, how the spiral thing? Yeah, Harini, is it clear for you, more? Yeah, med, yeah. So this is clearly like will be like this, but still these are complex, and these are not the kind of questions usually asked in the first time. Yeah, time later on, but I mean, because I mean, you're really asking something like, yeah, whether, but it's a good thing to think about, right? And there are so many possibilities. So it's not enough to check along all lines, but then again there are questions like, is it enough to check? These are very interesting questions. Is it enough to check along certain family of subsets? And there are families of, means that instead of checking for the entire ball, can we check along family of subsets, um, which will be enough? So I mean, can you check along like this piece, something like that, and make sure that's enough? That's enough not to check the entire ball, and that's enough to just check along certain special families. There are such things, but then those are again will go beyond our thing. Okay, and I think I don't even have much to say without preparing about that. Yeah, anyways, except for a few obvious things maybe. Okay, so this is fine, so we know the definition. Now what was the goal for today? um, right, so the goal is for these things is to, number one is deciding, and this is really a problem, right? Deciding when f is holomorphic or differentiable. See, because the problem is that there are so many ways you can approach H, right? So how do you really find out the limit? How do you decide whether f is holomorphic? This becomes a problematic thing because a function from C to C can be very complicated, and how do you understand? And then finding the derivative. Well, it turns out finding the derivative is in fact is easier once you know the derivative exists, because then again the usual rules of differentiability fortunately turn out that they apply. So finding is easy, but we need to decide, whether it's holomorphic or not, and that is really the goal. And for that we'll have to look at something simpler. Okay, so this is really the main goal. So for that we'll have to look at something simpler, and that is we'll have to look at functions from R2 to R2. Okay? We'll have to look at functions from R2 to R2 and look at a weaker version of differentiability, and then we will have a computational hold over what things are. Okay, but before I do that, um, there is another characterization of differentiability. There is another characterization of differentiability which again will be very useful, which will be the characterization we'll use to prove things. Okay, um, yeah, so let's come to that. So suppose this is something that you've already seen in reals, so I'll not prove it, but it will be just analogous to that. And in the complex theory, that's essential. Before you get to some real theorems, and from there you just use those theorems. But before that, it will be so. Suppose f omega to c is differentiable. Okay, So something very obvious I'll do, and this is at z naught. Let's say at z naught. So then this limit will be equal to something, right? You can just call it. You can call it a. Doesn't matter. Or maybe let's just call it what it is usually. It's f dash that naught. That. Now, as I did in the real case, we can just change things here and we can bring things like this. Right? And this becomes a h. So this is two complex numbers being multiplied. Okay, this is two complex numbers being multiplied. This is the again is the definition of differentiation. I have not done anything. But this means that this quantity you can is a function of h. Again, typically it is called psi h. Let's call it psi h. Okay, and then how can we then now just cross multiply and so on, and you'll get the following. F z naught plus h is approximated at f z, at z naught by the derivative h, and you have a function, right? This will get multiplied by h, right? So f z naught plus h can be written like this, right? This is the part that we are interested in. It can be written like the limit is not here. It can just be written like this, right? Because you just, I mean, this is just the definition, nothing else. But the key is that such that psi h goes to 0. I'm not done anything, just written the definition. This can be, this is the definition of derivatives also. Okay, this is the definition of derivatives. There's a big advantage to this definition. This is the definition that will help you to unify the theory of complex differentiation with real differentiation, which is because that's all we know basically, right? So because we are going to use that, there's something called the Cauchy-Riemann equation, which is our goal to get. That's the once you get there, then the whole plane opens for you to use it in all sorts of places. Okay, but we have to get there. Okay, first, right? So this psi h goes to 0. This is the key, and the thing is that this is a linear. This is not a linear, but you don't have division here. So as you can understand, this can be generalized maybe to R2 to R2. So that's the thing. Yeah. So now again, let's try to tweak this a little bit and see what we can say. Tweak this a little bit means that there is that complex multiplication that is going on between f dash z naught times h. We want to see that in terms of matrices. That is very essential. Okay, is that has later on also when you're doing Cn to C n-dimensional complex, you can see that will be essential there. But what we'll try to do is this multiplication, we want to see it as matrices being multiplied. Now, what is this? This is like a function from C to C where h is getting multiplied by, see, f dash z naught is a number. It's just a number. You people agree? It's just a number. So this multiplication to h is a function from C to C. Right? It is a function from C to C. Okay. Let's say, and the goal is to understand this via matrices, in terms of matrices. What does it mean in terms of matrices? Let's say that f dash z naught, soon we will have a very good this thing description of this in terms of partial derivative. Partial derivatives are nothing, I'll tell you, that's very simple. People might already know it. But let's say this was a plus ib. Let's say it was a plus ib. It's like two numbers, right? It's like two numbers, and this is also like two numbers, and the output is again two numbers. Right? It's like a 2 by 2 matrix getting multiplied with a vector and giving out a vector. That's what it is like, and I'm just going to tell you the details of that. So the really the key concept is very simple, right? So this is what it is, and we want to understand is via matrices. So the point is that let's say that you have a matrix. Let's say you have a matrix, okay, whose entries are, let's just say x1, x2, x3, x4, okay, such that, well, if one knows linear algebra, then one doesn't have to say anything here. One can directly write the matrix, but let's say we don't know and we're just doing it. So let's say that there was a matrix which was doing the same work of this complex multiplication, right? So we want to figure out if there is a matrix which will take the h as a vector and r2 and give out vector and r1. Okay, right. So how can we decide? Now we want to just decide these entries. I want to just decide these entries here. It's very easy. You can take special values of h. You can take h to be 1 comma. Take 0 comma 0, you don't get anything. Take h to be 1 comma 0. So if you take h to be 1 comma 0, then what is it that you get? You get x1, x3. Right? Just get the first column. Okay. Now what happens if you multiply a plus ib with 1 comma 0? What is 1 comma 0? It's 1. It's just 1. 1 plus 0 I. Right? Right. So then what do we get as the answer? We get a plus ib. Now from here, it's very clear that the x1 is a and the b is x3, right? This implies that the x1 is a, right? Because this output I must, so this input is this. This is the function which I'm trying to understand as a matrix, right? And the output is this. So it's a simple comparison. But this is slightly cheat way of doing it. There is a more conceptual way, but that will take more time. So I'm just trying to go through like this. And we just need it for 2 dimensions, so we don't have to really worry about the thing. X3, the X3 is B, right? So the X1 is A and the X3 is B. And similarly, if you do the other one, I mean, you know what to do. You have to just take 0 comma 1. Now let's do it. I mean, because I also don't remember it. So we'll see. Sorry. If you take 0 comma 1, then you get x2, x4. So anyone can calculate and tell me what x2, x4 should be. 0 comma 1 means this. Right, minus b plus ai, right? So this means that now I have to be careful. This is my first coordinate, is my x2. So it's minus b. So it's not just a matrix, but it's a very special type of matrix. It's a very special type of matrix. That is important, right? So you see, this complex multiplication, whatever it does to function from C to C, this matrix does the same to whatever the complex multiplication does as a function from C to C, which means it takes a complex number gives out a complex number. This matrix does the same thing, but it says it in the language of vectors from R2 to R2. But of course, these are the same things, in some sense, right? Same things. This is a good strategy as well. So sometimes you may be given a matrix, complicated matrix, and it's what is known as linear transformation. But at the end of the day, you can just interpret it as complex multiplication, and then that might make life very, very simple for you. Yeah, try understand my point. So this is a good strategy that there is you can go back and forth between these two things. Okay, from a matrix you can understand the multiplication as numbers, like as complex numbers, and vice versa. Okay, so now we'll remove all these things and we will just write the matrix. So complex multiplication can be seen as a matrix multiplication. Yeah, that's what it is. So in fact, any type of multiplication can be seen like that, because multiplications are some sense they're linear. Um, yeah, right. Because of this, basically the distributive law that allowed us to. I mean, this is still incomplete for a lot of reasons, but you can check that. you can check the incompleteness. So why is it incomplete? Because you have to still check that it really works for all other values. I mean, I have only checked it for two values, right? What you have to check is if you take a complex number, if you take a complex number x plus iy, right, then this should give you the right answer. This answer should be right as you would get multiplying it plus ib. But I'm sure you can check.
Let it be a linear combination of these two vectors, right?
Yes, that is, if you see it like that, then yeah, then you don't have to think about it. But yes, that's right. It is only linear and that's the reason why it was enough to check for these two vectors. Okay. Yes. So the whole multiplication is determined. The whole multiplication is determined by understanding it for 1 comma 0 and 0 comma 1. That was the point. Yes. So I think that is good observation. Um, right. Yeah. Why am I doing this? Sorry. Right. Okay. So this is fine. And yeah. Yeah. So now we can, okay, so how do I go about this? It's just I'm trying to curate my own way. Stein and Shakarchi doesn't mention all this like this, but I'm just trying to say it in a way that will make more sense to me. Because when I learned complex analysis, it was quite fast, and I didn't get the time at all, and I didn't have understand these things. I mean, I just got to the Cauchy-Riemann equation and then move forward and so on. I never really. So I was trying to basically ask myself, like, why do we do this and so on, and prepare the class. Okay, so this thing, okay, now what is it that we want, like this thing? So now we can frame this definition, we can frame this thing as, instead of this f, I mean f dash does not, we can just say that there exists a matrix, right? I mean, this can be treated as a vector in R2, right? There exists a matrix A, there exists a matrix A such that this happens, right? And by this happens, I mean, you can consider all these things as tuples of numbers rather than, know, rather than as complex. Yeah, so that's equivalent. There exists a matrix, but obviously not any matrix. This has to be a special type of matrix, right? See, whenever you can find a matrix that satisfies this equation, when you consider everything as vectors in R2, and if that matrix is of this form, then you can go back and say that, yeah, this multiplication corresponds to a complex multiplication. Not every type of matrix will correspond to a complex multiplication. It has to look like this. And if it looks like this, then it is A plus IB. That's also very clear. And if it does not look like this, then you can show that I mean, you can check that it will not correspond to any complex multiplication. So it is very important that it be like this. Okay? This will be essential for us. Right. So this matrix view is what one uses when you do from R2 to R2. Okay. So let's say you have a function f. Yeah, any questions? Okay. So let's say you have a function f. Now what I'm doing is I'm breaking this into two functions. Okay. U and v. Because that's how functions from R2 to R2 are. They're just two functions. They're two functions with two variables. Of course, I can't separate these two inputs. They can be mixed in very strange ways. So I usually cannot separate them. But it will be two functions, right? Even this f, I mean, I can just right away, I mean, from the start, I should say, rather, right from the start, I should have said that f is uxy, sorry, uxy plus I. Yeah, this is how we can look at our f. I have to put the I there because I'm looking at it as a complex thing, right? So now I want to understand what it means for this kind of function to be differentiable. Okay. Now here I'm not going to write out a definition straight away, but we are going to motivate the definition. Okay. Because again, there are many kinds of derivatives. As I had done in the real case, we had seen that there can be different types of derivatives, and it is really in the end what you want to compute is how you make the definitions, right? Um, Of course, it has to have good mathematics also, in the sense that must behave well, must have the usual properties and so on. But it really depends on what you want to compute. So what function? Let's take an example, right? Let's take an example. So let's say the function is, so here we are trying to define differentiation R2 to R2. Okay, we have to understand how should be defined. Should we just differentiate with first variable and second variable and just return two numbers? Essentially, that's what we do. To be, if you're doing an engineering course, then that's what you do, and that really just works also. But of course, one has to show it and so on, so on. We'll see. Let's take an example. So we will, um, yeah, we will take, let's say, take this example. This comma, you can take the other point to be anything, but the point is I'll just focus on one of them. I'll focus on one component at a time. Okay, we will focus on one component at a time. And see, this is really everything. Everything here is that if you're looking at a function from R2 to R2, right, then the two components are completely independent in general, right? Pragmatically speaking, these two are different. They are not related, but usually they are in some context and they'll be related. But usually they are, sorry, theoretically speaking, they are not. They don't have to be related, right? But where does it differ from complex numbers, right? When you're looking at a complex function, okay, you're looking at a complex function. Let's say this, which squares this. Of course, you can look at it as a function from R2 to R2, right? But so there's one mistake I was making in, not what I said today, but what I was thinking about some time back. Okay? But anyways, when you look at a complex function and you square it, right, you will see that usually what happens to the real, when you separate the real and the imaginary parts, you will see that they are sort of coming from some place where they were together. Right? They were together in some place, and from there they are coming. You see my point, right? They were together in some place, and from there they're coming. So these two are related in some sense if you're looking at it as complex, right, functions. And that is a reason, I mean, that's the reason why if you take any function from R2 to R2, can you write this as a function from C to C? Meaning that can you write this as, can you write this in terms of x plus iy? That's the question. Can you write this expression in terms of x plus iy? Right. So
We don't want the component to imagine power.
yeah, that's right. You can do it. You can say it like this. But now, I mean, can you write this as in terms of x plus iy? Because the input was, let's say, x plus iy. Right? So you can't. It's maybe in this case you can by some manipulation, but you cannot combine them in general. Point, you understand, right? You cannot write this in terms of x plus iy. You see, I mean, you may need to use x minus iy. Then you can surely write. Then you'll have z and z conjugate. So what I mean is, you can write this like this: z bar plus, okay, what will this be? You can again do something there and do it. And x plus iy,
Write it as x plus iy the whole square.
x minus iy whole square. Yeah, so you can try it. You can do something like that probably. Something like this you can do. But you're introducing a z bar. You cannot write it entirely in terms of z. I think this one, right? So that's my point. That when you take functions from R2 to R2, in some sense there are many more functions from R2 to R2. They're not related. The real part and the imaginary parts are usually not related, and you cannot really combine. I mean, see, you can say this is a function from, but can you say that this is a function from C to C? Yes, you can say. I mean, you cannot hold me. Yes, you can say. I think you can say this is a function from C to C. You're just conjugating another, taking an input and conjugating it. You can say that, but it's not a natural thing, right? It's not like z bar is coming. A z bar we know is not even differentiable. So maybe if I should ask, can you write this as a in terms of z in a differentiable way? And you'll see that it's hard, or maybe the answer is no. That's my point. Okay, that you cannot always combine. So these are many more, and here it's more looser. Okay, but if you are taking a actual complex function and breaking it up, then the parts, of course, you can combine back. That's the subtle difference. Means the usual functions mean good function means which are differentiable, which we don't have z bar and so on. Okay, let's come back to this aspect of defining differentiability. Okay. So again, I'll just do it on basis of components. We'll do it a component at a time. Otherwise, one can also just write out a definition in terms of matrices. That motivation will also somewhat have. But if we just look at yeah, we just need to, we have the notations. If we just look at this and try to come up with a definition of differentiability for this. So first, let us try to understand what we are trying to calculate. So if we pose the problem as we are trying to calculate the slope of the equation of the tangent line. Okay, so let's say at, take the simplest non-trivial point, let's say 1 comma 1. Roughly the graph you can understand, it's good to understand these graphs because you can then apply Jensen's and so on in two variable case also, in the sense that for these kind of functions for which you may not know if their second derivative is, because second derivative of a two variable function is something, is a Hessian of something, determinant of some matrix. But this function, let's say it's like this. Okay, I think this is not a good picture. It should be more like maybe more like a cone, right? More like, no, it has to already start going up. Something like this, right? Yeah, it should be more like this than this. Yeah. So it doesn't go down. You can understand, right? At every cross section, it is like this, kind of. Okay. All right. Okay. That's good. That's good. What are we trying to do? You pick a point, let's say 1 comma 1. So let's, yeah, be very clear with the axis. So we are simultaneously also trying to understand these things, what differentiation means for two variable functions. So you pick a point, and this is 1 comma 1 somewhere here. So it's 1 comma 1 comma 0, but it's 1 comma 1 on the plane. The value would be something not exactly important, it's 2. So it will go up somewhere on the curve at height 2. Now our goal is quite clear. Our goal is very clear. We want to understand the derivative of this. I want to define the derivative. Sorry, you want to understand the slope of the tangent. You want to understand the equation of the tangent, right? So I mean, will not go into finding the equation of the tangent. That is not very. I mean, that's not a calculus problem. That's a different kind of question. It can be done, but the point is, how do you define the slope of the tangent? That's more important, right? So let's say the tangent. So this is t. T is tangent. Now again, this needs a definition, but we sort of understand. Let's say it's the plane which is the best approximation of the curve. Best approximation by any plane. It's a best plane, sort of. We cannot use things like intersects at one point. Even though in this case it will intersect only at one point because it's a convex figure. You can see it's kind of just if you take a tangent, but tangent in quotes. Obviously in the end the matrix we define will sort of will sort of lead to the definition of the equation of tangent. But yeah, but the point is that, let's say this is a tangent. How much information does a tangent need, right? So if you think about it, um yeah, what do you think, yeah, so for a tangent I would say, so let's say you're trying to find the equation of a tangent, right? It will typically be like this. I mean, that zero is, I have made it zero because I have made it zero because the point, one of the points on the tangent, so you can shift it at the origin. That's not a problem. You can shift it at the origin by, yeah.
Why is differentiation necessary for finding tangents in this space? Like we can find the normal vector at that point.
No, you cannot find a normal vector at a point, right? If you don't have a tangent, then what does normal mean? Not yeah, but then how do you define that? That is the whole problem. For a curve, for a two-dimensional curve, what's the position vector of the normal at the point? That is the same problem as this, right? Same. But then how do you define that? That's the thing. So we have the tangent, and it is at the point. Well, it's not 1, 1. It's actually 1, 1, 2. Since we know one of the points, I just assuming you can shift it to the origin. That's not a problem. But in the end, this will become something like this. Now, how much information do you need? You need two informations, right? Because I mean, you can always make one of them one. You can make this C1 by dividing out, right? You can write this as A by C X, B by C Y Z. You just need two pieces of information. Right? We need two pieces of information, and we will see what are they exactly, and they will be the partial derivatives, but we'll come to it naturally. So yeah, so what I will try to do is, if you want the equation of a tangent, if you want to understand the tangent, we will take sections of the tangent which are in 2 dimensions, not in 3 dimensions, right? What do I mean? So let's say that you take, so you have the point 1, 1, 0. For a second, let's stop varying the y, the values of y, okay? Because we're trying to, what are we trying to do? We're trying to get two tangent lines. You see, we're trying to get two tangent lines on this, something like this, and one of them like this, and that they are enough to give us the plane, right? And that will be enough. So geometrically, also two pieces of information are enough. I don't know why I went into this business here. Not necessary. You just kind of need two vectors on the tangent line, on the tangent plane, sorry. You need two vectors on the tangent line. And what are the two natural choice of vectors? We'll see. So you fix the y coordinate. So you fix the y coordinate for the function, and you only vary the x coordinate, okay? So you fix the y, you can fix the y to be 1. You can, means for the time being, you cannot actually put it 1 if you just put it as y, but fixed. Wait, does it that's 1 second, let me think. No, it will matter. So will it not matter? Anyways, it doesn't matter. Let's see. Yeah, so you fix it at some y naught. It's 1. Okay. Now if you only vary the x, yeah, if you only vary the x, then what do you get, right? You get that's a little, 1 second. Yeah, if you yeah, if you only vary the x, right, then what happens is you can essentially take a perpendicular, right? You can take a perpendicular at this point, right? And what you will get is a two-dimensional version of this function, like this. I mean, this blue line will be on the green curve, right? But it is on this section. So I'm taking the curve, simply put, I'm taking the curve and taking its intersection with this vertical plane. I mean, I can just say what the plane is: y equal to 1, y equal to y naught. Y equal to y naught is better, I think, right? So taking y equal to, sorry, taking y equal to y naught and taking its intersection with the curve. That's basically what I'm doing. I'm fixing the y. It's very obvious. I'm fixing the y and I'm taking the part of the curve. It will be, this is now just like the function fx going to x squared. The y is fixed, right? This is this function basically becomes fx going to x squared plus some c. That c is basically what is lifting it up, right? Otherwise it would just be fx going to x squared like this, just the usual fx equal to x squared. If you just push it back by y naught units back to the xz plane. right? You can actually do that, right? I mean, in fact, we have to do that to say it formally, right? So my point is that what do I want to say formally? I want to understand the the vector that is tangent to the blue line. Okay, if I want to be formal, I can say I want the intersection of t with this line, intersection of t with this line, with this plane. Sorry, is that right? That's essentially what it is, right? You take the tangent plane and you take its intersection with this line. What you get is a with this line, with this plane. So you take the tangent plane, sorry, you take the tangent plane, you take its intersection with this vertical plane. I've made it very complicated. It is not so complicated, sorry. You take the tangent plane, you take its intersection with this vertical plane, right? And you get a piece of the vertical plane that's tangent to the curve, right? And we know that that piece is essentially fx equals to x square plus some y naught square, some constant, right? So this tangent line is the tangent of the function ux equal to x square plus y naught, which is equal to the tangent. I mean, the tangent of this will be same as the tangent of, I can just say gx equal to x square. Is that right? I mean, that this doesn't matter, right? It's the same thing. The y naught square will not change the slope. It's basically like pushing it back, projecting it back on the xz plane. See? So this tangent vector, I mean, the vector will not change, right? The vector will not change. The vector, the head and tail of a vector don't matter, right? As long as they have same length, the same slope. Um, yeah, you can take unit vector in place and so on. But yeah, the point is that the slope that you get, that is one piece of information. And then, yeah, what is that? That is the derivative of this function, or in some sense, that is a derivative of ux when considered as a function of x. That's the derivative. So in general, is that right? In general, this would be the derivative of the function u of x comma y, but when this is just considered as a function in x, and that's what is the definition of partial derivative. Is that right? So this is what I need in my definition of derivative, this piece of information. And then similarly, the second piece of information would be taking the derivative of this with respect to the, and this is nothing, just treat the first variable as absolutely constant. Okay. It doesn't mean it will always be 0. Sometimes it may feature in, if it's a y here, then it would still feature in here, somewhere like that. But of course, it's a constant with respect to y. These are the two numbers that I want, because these two numbers will give me my plane, right? These two numbers will give me my tangent plane. So I want these two to be in my definition. Okay. So we know what we want in our definition. Now, how we are going to put it, that we'll see the next time. And yeah.
We are this lighting thing which we are experimenting this thing.
Hmm.
Is it what we call contour or something like that?
Is it what we call? Um, is it called? No, contour is usually a closed thing, I think. Right? Contour will usually be a closed thing, and yeah, contour is a closed thing. Contour is a closed thing. It's a closed curve, which is a function from R to R2. So it's a path in R2 which you're trying to parameterize with respect to time, and you sort of get a contour, but it has to be closed, I believe. And then you look at points, singular points inside, outside, and that helps you to actually give the integral. That's the magic of complex analysis, which we'll see later
In a plane like z equals to z naught or something like that,
on.
or
Hmm.
maybe some inclined one. So the projections of that vector which we will get on that plane, will that be contour?
That I don't know why it should be a contour. The definition of contour should be, yeah, it has to be a closed thing, I guess. Number one, as far as I know. I mean, the contour has to be closed, right? Even if it's done topography and geography, right? Contours are always closed. Right? Contours have to be closed. Yeah. So that's a different thing. No, contours are different. Not every closed thing you draw should be parameterizable with time or with one dimensional thing. No, so I do not think it will be a contour. Okay. But is it clear that why partial derivatives tell you the whole picture? That is important, right? Tell you the whole picture about the tangent. So these two are the things which will be in our definition. In fact, these two will be the only things in our definition. Okay, we'll see. We'll continue this the next time. Yeah. Any other questions regarding what we did today? Mm, no questions. Okay, then that's it. I think on Thursday we'll have a